Welcome, everyone. Thank you for coming back for another video in our series on the analysis of variance. This video builds on our first video, Variance, a Refresher, where we went over the basics of variance. Today, we're going to introduce new topics that will help you understand ANOVA. To start, we will quickly go over some points from the Variance Refresher video. This will help us all start from the same place as we move into today's new topics. In this video, we'll cover some basic statistical concepts that are key to ANOVA. These include random sampling, statistical estimators, expected values, and unbiasedness in estimation. We will not only explain what these terms mean, but also demonstrate why they are important with the help of statistical simulations. We'll start with random sampling and its crucial role in statistical analysis. Then, we'll explore statistical estimators, explain what they are and their significance in ANOVA. Following this, we'll delve into the idea of expected value and its impact on the precision of ANOVA outcomes. Lastly, we'll examine the concept of unbiasedness in statistical estimation and its necessity for ensuring dependable and accurate data interpretations. Thank you for joining us in this video. Let's get started. In this video, we'll be introducing you to a statistical simulator that's going to play a significant role in our upcoming lesson on random sampling. Using this tool enables us to take a unique approach to statistics, a shift from the traditional methods you may be accustomed to. Often, traditional education in statistics requires us to accept certain statistical concepts on faith because they are not easily demonstratable or directly observable. These elements can be challenging to comprehend, especially for new students. However, our simulator offers a more intuitive way to grasp these concepts. Our simulator enables us to directly alter and then display the true population parameters before we perform any statistical operations using the population data. Usually, when we perform statistical analyses in the real world, we don't have access to the true population parameters. If we did, we'd simply measure their values and form our conclusions directly. Instead, we have to take samples and make inferences about the unknown values of the population based on those samples. This is how we create our estimates of population parameters like the mean or standard deviation. We then use these estimates to draw conclusions about the population. However, a simulator provides a different perspective by allowing us to visualize the complete population from which the samples will be drawn before we start the sampling process. While this information is normally unknown to us when we conduct statistical tests, having it visible will facilitate our understanding of the relationship between a population and samples drawn from it. To begin with, take a look at the first column of scores on the simulator, which contains the population data. Although we can only display 43 of the scores on the screen at one time, the full column actually contains 2,000 normally distributed scores which will serve as our population. We are able to set the mean and standard deviation of the population to any value we want, observe the distribution of scores, and see how samples taken from this population actually reflect the population parameters. Similarly, as we demonstrated in our previous video on variance, we can also vary the variance and observe its effect on the dispersion of the population distribution. This provides us a practical way to simulate these complex statistical concepts, and we can repeat this process as many times as we want for additional clarity. Let's take a look at the simulator. We'll begin by revisiting some concepts we discussed in our previous video on variance. We're going to illustrate what occurs when we set the population variances at different levels. We are starting with the population variance set to 0. As we explained in our video on variance, if a population has 0 variance, all scores should be identical, and this score will be equal to the population mean. In our simulation, with a variance set at 0 and a population mean at 100, all scores in the population are indeed 100. As predicted, there is no variance in the scores. Obviously, if we were to select a sample from this population, all the scores in the sample will likewise be 100. Now we'll show you how our simulator can manipulate the population means and variances, which will enable you to observe the effect that these changes will have on the full population and samples drawn from it. Let's start by setting the variance of the population to 1, which is a very small amount of variance. Pay close attention to the population scores as we make this adjustment. You'll see the scores change. They're no longer strictly 100. They vary on both sides of the mean. Moreover, because the variance is so low, these scores are tightly packed around the mean of 100 with minimal variation. Next, we'll make the population variance larger by setting it to 225. Now, observe the population scores. They're significantly more dispersed around the mean of 100. You can clearly see that the larger the variance, the more spread out the scores in the distribution are. We'll now use this feature of our simulator to demonstrate taking random samples from a distribution where we know what the true mean and variance actually are. But first, let's briefly define what we mean by a random sample. A random sample is a subset of items selected from a larger population. What makes it random is that each item or person in the population has an equal chance of being chosen. Because samples that are randomly selected will in the long run be representative of the population from which they were chosen, in an ANOVA, random sampling is crucial to ensure that your results are generalizable to the larger population. We will have more to say about this shortly when we discuss expected values and unbiasedness in statistical estimation. Before we move on to our full simulation of random sampling, here is a hypothetical scenario which will help make the concepts we will be discussing more concrete. Suppose you're a psychology graduate student collaborating with a professor studying the reaction times of college athletes to visual stimuli. The university provides a list of 2,000 athletes on athletic scholarships, and your goal is to determine the average reaction time in your lab. Given the size of this population, it's impractical to measure everyone due to constraints in time and resources, leading you to adopt random sampling. For our simulation, we have an edge not typically present in real-world research. We know exactly what the mean and standard deviation of the entire population is before sampling. With this data, we can evaluate how accurately the sample represents the actual population parameters across different sample sizes. Let's initialize our simulation with an assumed average reaction time for the full athlete population of 250 milliseconds, alongside a standard deviation of 30 milliseconds. Consequently, the variance, standard deviation squared, is 900 square milliseconds. These values serve as the initial parameters for our simulated population, representing the reaction times of all athletes if we had the capacity to measure everyone. From this simulated population, we can now draw random samples of any size and make inferences about how well these samples correspond to the actual population values. For this demonstration, we'll pull multiple samples of identical size from our population. This process illustrates the concept of sampling fluctuation, the variability that arises when we draw multiple random samples from the same population. Starting off, we'll draw a sample of 5 athletes. Examining the first sample, we see that the reaction times of the 5 athletes selected vary as one would expect. Different athletes naturally have different reaction times to visual stimuli. The reaction times of the athletes randomly selected in this sample ranged from about 226 to 303 milliseconds. The mean reaction time for this sample is about 256 milliseconds, with a standard deviation of about 32 milliseconds. Drawing a second random sample of 5 athletes, we observe reaction times ranged from about 251 to 298 milliseconds. The mean reaction time for this sample is about 265 milliseconds, and the standard deviation is about 19 milliseconds. Notice the discrepancies between the two samples. Each sample provides a unique portrayal of our population, highlighting the principle of sampling fluctuation. Though both samples originate from the same population, random samples can result in noticeable differences. In particular, notice that the means of the samples are different in spite of the fact that they were both drawn from a population with the same mean. This is sampling fluctuation and is anticipated and always present when we draw multiple samples from the same population. Now we will draw another random sample from the same population, but this time we will increase the sample size from 5 to 30. The athletes selected in this sample had a mean reaction time of about 249 milliseconds and a standard deviation of about 26 milliseconds. The reaction time of the 30 athletes selected ranged from about 182 to 299 milliseconds. Let's take a second sample of size 30. The athletes selected in this sample had a mean reaction time of about 244 milliseconds and a standard deviation of about 27 milliseconds. The range of the reaction times was from 193 to 298 milliseconds. What can we conclude by comparing the 4 random samples we selected? First, none of the sample means were exactly the same as the population mean of 250 milliseconds. The 2 samples of size 5 had means that were higher than the population means, while the 2 samples of size 30 had means that were lower than the population means. Likewise, none of the sample standard deviations were exactly the same as the population standard deviation, which was 30 milliseconds. Sample size didn't seem to result in an obvious superiority regarding how closely the sample statistics matched the population parameters, at least for the 4 samples we drew. Normal sampling fluctuation created differences among the means and standard deviations of all the samples, and none of the observed values exactly matched the population values. So this raises the question of whether there is a tangible benefit to adopting larger sample sizes, considering the increased time and expense that taking larger sample sizes creates. The answer to this question is that there is a critical distinction between taking samples of size 5 and size 30, which is not apparent when analyzing each sample in isolation. The more important question is understanding how close the mean and standard deviation of our sample will be to the true population mean and standard deviation in the long run, over multiple samples. This question is nearly impossible to answer accurately by examining the values that obtain from our samples in a real experiment, as we never know what the true mean and standard deviation of the population actually is. However, by using our simulation, we can get some idea of how different sample sizes affect the likelihood that our sample statistics closely approximate the population parameters. We will answer this question in the next section of our video. If you would like to take a break, now would be a good time to do so. Pause the video and resume when you are ready. Each time we take a random sample, we are making an estimate of what the true population values are. So if we calculate the mean of a random sample, that sample mean is our best estimate of what the mean of the population is. The same holds true for the standard deviation or variance of a random sample. They are the best estimates of the actual population standard deviation or variance. Because of this, we refer to the mean and standard deviation of a random sample as statistical estimators because they are the best estimates that we have of the unknown population values. In a moment, we will explain why this statement is true. We have seen that due to normal and expected sampling error, these sample values will usually be different from the true population value and different from each other as well. So how do we know how different they actually are? You have likely learned in your statistics course that one way to estimate this is by calculating confidence intervals around the sample mean, which will give you a range of values within which the true population mean likely lies. We will not be reviewing how to calculate confidence intervals in this video. Rather, we will answer this question via simulation instead. Practically speaking, we only will be taking a single sample from a population when we conduct a study. For instance, in our reaction time study, we might only take a single sample of the population of athletes to estimate what the reaction time of the total population is. But what if we could take multiple samples and average the results obtained from each sample? Would that give us a better estimate of the true population value? The answer is that it would. In fact, the more random samples we take and the larger those samples are, the better the estimate will be in 2 regards. The first is that the estimate of the mean of the population will most likely be closer to the true mean of the population if we average the means of many random samples. Second, even if the mean that we calculate by averaging the mean of many random samples is not exactly equal to the mean of the population, the amount by which it differs from the true population mean will likely be smaller than if we just use the mean of a single sample for our estimate. So now you may be wondering, how many samples would we have to take to get the closest possible estimate of the true population mean? The answer to this question lies in a theoretical statistical concept known as expected value. The expected value is the long-run average value of a random variable over an infinite number of repetitions. An example will help to clarify this definition. If we took an infinite number of random samples from our population of athletes' reaction times, calculated the mean of each of these samples, and then averaged all those sample means together, the result would be the expected value of the mean. It turns out this expected value would be exactly equal to the mean of the entire population. So we can say that the expected value of the mean of any random sample is exactly equal to the population mean. While any single mean of a random sample will vary from the population mean by an unknown amount due to sampling fluctuation, the mean of an infinite number of these samples will always be equal to the population mean. This holds true for any sample size. This allows us to say that the mean of a random sample is an unbiased estimator of the population mean. It is unbiased because its expected value will be exactly equal to the population mean from which those samples were drawn. This is the justification for using the sample mean as an estimate for the population mean when we draw conclusions from statistical procedures like ANOVA, and why an assumption of most inferential statistical tests is that the samples being tested are random samples from the population of interest. Even though it would not be possible to take an infinite number of samples, we still can use our simulator to take a large enough number of samples to demonstrate how sample size and the number of samples taken affect the accuracy of our estimate of the population mean. Here's how we are going to do that. We're going to use our simulator to draw 25 random samples, each of different sizes, from our population of the athletes' reaction times that we have been using for our other simulations. The population has been set to have an average reaction time of 250 milliseconds, with a standard deviation of 30 milliseconds. Our first step is to draw 25 different random samples, all of size 5, from this population. We'll then calculate the mean reaction time for each of the 25 samples. After that, we'll calculate the average of these sample means. We'll also calculate the range of the sample means by subtracting the smallest mean from the largest. This will give us a sense of how much variation there is among the means. We'll then repeat this process with another batch of 25 random samples of size 5. After that, we'll draw 2 groups of 25 random samples of size 30, and then 2 groups of 25 random samples of size 100. All the results from these simulations will be collected and displayed in a table on the right side of your screen. Looking at the summary table, we can answer our initial question about the influence of sample size on our estimate of the population parameters. The table demonstrates that the average of the means of 25 random samples provides a solid estimate of the true population mean, irrespective of the sample size. For instance, the average of 25 sample means of size 5 was 250.96, very close to the actual population mean of 250. This similarity holds true across the averages of the sample means, regardless of the sample size. In fact, the average of the means of 25 samples of size 100 did not produce a substantially better estimate of the population mean. But before you conclude that sample size doesn't matter, let's remind you why our results from the simulation turned out the way they did. Remember that the long-run expected value of a sample mean randomly drawn from a population will always be equal to the true population mean, regardless of sample size. But this does not indicate that smaller sample sizes provide as precise an estimate of the population mean as larger sample sizes do. In fact, the truth is exactly the opposite. Larger sample sizes will provide more precise estimates than smaller samples. Remember, when conducting a study, you will generally not be drawing a large number of random samples from the population averaging the results. You will be likely drawing only a single sample. Therefore, you will not get the statistical benefit of averaging the results of a large number of samples to estimate the true population values. Also, you generally will not have any way of knowing what the true population values are, so you will not be able to directly determine how close your sample mean is to the true population mean, except by statistical probability estimation. Let's examine the column labeled Range of Sample Means. As a reminder, the range of sample means is calculated by taking the largest sample mean and subtracting the smallest sample mean from it. This gives us a rough indication of how much the sample means vary from each other. We can see that the range of the sample means decreases dramatically as the sample size increases. You can see that the difference between the smallest sample mean and the largest in the first sample of 25 means of sample size 5 was about 67 milliseconds, while the difference in the last sample of size 100 was only about 10 milliseconds. Now let's look at the 25 sample means that were calculated from our first sample of size 5. You can see that the smallest mean was 217.84 milliseconds, and the largest sample mean was 285.18 milliseconds. So if you were drawing a single sample of size 5 from our population, you might have ended up with any one of a huge number of possible random samples like the ones listed here. Perhaps you might have drawn the sample with a mean value of 249.41, which would have been very close to the true population mean of 250, but you also might have drawn the sample with a mean value of 285.18, which is very far away from the true population mean. Whatever sample you drew would serve as your best estimate of the true population mean. Although we haven't covered the central limit theorem yet, When we do, you will learn that the distribution of sample means, like the ones you see here, will be normally distributed as long as the population from which you drew the sample was also normally distributed or the size of your sample was at least 30. Therefore, statistically, you will be more likely to draw a sample that is closer to the middle of the distribution than a more extreme sample. But you would never know exactly how close or far away your sample value was. But what you can see from the simulation is that a small random sample size of 5 would provide a very imprecise estimate because the range of possible sample means is so large. Let's compare these results to the first group of size 100 samples we took. The average of these sample means was 250.33 milliseconds, which is very close to the true population mean of 250 milliseconds. But let's look at the range of the sample means. You can see it is 12 milliseconds, which is much smaller than the range for the samples of size 5. Now let's look at the actual means of the 25 samples of size 100. You can see that the means are all more closely clustered around each other. They vary a lot less than the means of samples of size 5 did. So if we took a single sample of size 100, the worst likely outcome would have been to draw a sample with a mean of 244.41, which is very close to the population mean of 250. At the other end of the scale, we might have drawn a sample as large as 256.41, which is still very close to the population mean. The conclusion from these simulations is that the larger the sample size, the more confident you can be that the mean of the sample that you drew is a good estimate of the true but unknown population mean. Larger sample sizes will provide more precise estimates of the population mean on average than smaller sample sizes. Thank you for watching our video on random sampling. We hope you found it informative. Our future videos will continue to supplement your classroom instruction in statistics. They are designed to reinforce your learning in topics necessary to fully understand the topic of one-way analysis of variance. Future videos will be covering the central limit theorem, the meaning of experimental error, the factor model of individual scores, and finally, one-way analysis of variance. Thanks again for watching.